Welcome to queenon7.com. Please like, share and subscribe my video. We're gonna look at the Arrhenius plot today. If you remember in the previous video where I have explained what is an Arrhenius equation and why he has developed Arrhenius equation, I just want to add few things. You do remember the equation for the straight line. In this scenario, when we actually plot 1 over t, which is actually the temperature against the rate constant, and you will get a line, a straight line which is going down. It shows you that by increasing the temperature, the rate constant will decrease. So obviously it can go up or down based on, it depends how the straight line is going up or down. So we have that sort of relationship at the moment. Now, the reason we are plotting 1 over t, we can actually plot just temperature. A lot of people actually ask about that. The reason we actually plot 1 over t, because we are going to use the equation of straight line. Now, if we use that, y is y-axis, which is actually log of k. Then m is obviously EA over r. So that m is EA over r. X, which is x-axis, you have 1 divided by t. So we can't just plot t there and put the value there. So you have to have in the same form. So it's 1 over t. So we can write this one down as 1 over t. So x is actually 1 divided by t. So which is the part of the EA over RT. Then you have c, and obviously you have a log of a in there, so we put minus there because it's minus a. It will be log of a. So you can be asked to calculate activation energy, or you will be asked to calculate a. Now a is actually representing what are the factors which depend on a. So technically all these relationship or the Arrhenius equation give you information about the static effect and the collisions. That's what I have already said in the previous video. But for A levels, you don't need to know. But just for in the back of your mind, that this is what it is. That it gives information about how many molecules are going to actually collide with the right orientation to achieve the activation energy. Now, this equation we're going to use, and we are going to use this in the simplified form, or called linearized form, to actually calculate EA or A itself, which is Arrhenius constant or pre-exponential term. If I actually draw that, a point like this, and I say, what about this EA over R? EA over R is actually a gradient. So if you see my GCSE video where I've already explained that how you actually use the slope and you draw a tangent and complete the right hand triangle, and then you divide y by x to calculate the gradient. In here you have the gradient, which is actually equal to minus EA over r. That's what it is. Now what I'm going to do is I will be actually using this as a part of calculation. So if I will actually say this is 3 minus 3 minus 4 minus 5 minus 6 minus 7 if log of k is going this way, and the temperature, now the temperature, because it is 1 over t, most likely it is in the Kelvin, like 330 or 400 Kelvin. So your temperature will be actually in points. So to handle the temperature, rather I would say I have a temperature 1 divided by 350, and you get a value of 0.3 something 10 is 3.0 10 is power minus 3. We try to handle it like this. So if this is 3, let me see how I can do that. So if this is 3.0, this is 3.1, this is 3.2, 3.3, and so on. Now I'm going to remove this because you already know the gradient, which is obviously the obtained from there, is equal to the minus EA over R, not T. So in this case, all I'm going to do is I'm going to calculate the EA first. So the relationship is there already. All I have to do, I have to calculate gradient. So if I pick a point, for example, if I pick 2 points there and I try to create a triangle there, and I will see that if this is y and this is x, the gradient obviously is equal to y divided by x. If y is actually 1 and x is between the 2 points, obviously 1 point, obviously the temperature is actually times by 1.1, it's 1.0 10 to the power minus 3, sorry 1.1, or is it 0.1? I'm just going to look at, yeah, it's 0.1 because it's 3.0, 3.1, so it's 0.1 is the space between each other, and 10 to the power minus 3 because it is actually 1 over t. So if it is 0.1, 10 to the power minus 3, I would take that from here. If it is like something like 0.12 or 0.11, 10 to the power minus 3, if it is not equal, it is going to come around 11,000, the gradient. Now if I use this, because this is in minus, and you are going to use that in minus anyway, 1.0, so if I put minus there, so that's going to be minus 11,000. So obviously it is in the minus, so I forgot to put minus there, so you have 1.0 and divided by the x, the value here, which is 0.11, 10 to the power minus 3. It can be 0.1, but I'm just doing a rough estimate. It's going to be around minus 11,000. Now using this relationship, if you rearrange this relationship, you will say the minus gradient, whatever the value is there, times r. So minus the gradient is already given, minus 11,000 times r, 8.314, and your answer will be, when you simplify this form, and that's gonna come around 91410. So 91410, and that's gonna be joules per mole. You can convert that into kilojoules per mole, which is 91.4 divided by 1000, so it's kilojoule per mole of energy. Now once you have done that, you got EA, and you can actually, and you got the gradient obviously as well. The gradient is exactly equal to EA over R, the value there, and which is actually, we have at the start we said the EA over R itself equal to the gradient, which is actually this value. This is the gradient, so we can use the same value to actually put into the linearized or simplest form of the Arrhenius equation. So if they ask you calculate EA, that's what you're going to do. You're going to draw a triangle, and then you're going to do y divided by x, and you actually put into the value for the gradient. You get the gradient, you put into the formula where at the start I said gradient is equal to minus EA over RT, because m is the gradient in the straight lines equation. Once you've done that, they can ask you calculate Arrhenius constant, or you can say the pre-exponential term. A. So you want to calculate A. So what we're going to do is we will look at the equation. The equation you already got there, so you have to simplify it. So log of A is equal to log of K plus EA over RT. Log of K is obviously, now you need to pick one point. So if I pick one point from here, for example, if I pick one point from here, 3.2, and I against 3.2 I have 5, so I will put 5 will be the y-axis, which is a log of K, so I will put minus 5 there. And then I have what do you call it as x, obviously 3.2. I'm going to use that in a minute, but I need to use this one. This gradient is equal to EA over R. EA over R is equal to gradient, which was equal to minus 1.0. So minus 1.0 divided by 0.11 10 to the power minus 3, and then, which obviously minus 1000, and then you have a t. Now 1 over t, I don't have to write down 1 over t. What you can do, against 5, which is y-axis, at 5, what is the value of 1 over t? So that is 3.2. So you will be putting here along with this. You're going to put there 3.2, so times 3.2, and I'm pretty sure once you do that, you can actually now solve all of this. It's gonna come around, if I'm not wrong, it's gonna come around 31 or something log of a. I do not have calculator, so it's gonna be something 31.0 or maybe 31.8 or 31.9, something like that. It's gonna come. Once you've done that, you take anti-log of both sides. You have that, so you will e 31.0, and the answer will be around 1.19 and 10 to the power minus 13, which is dm cube per mole per second is the answer for this. So this is how you actually use that. So you plot the graph, which is actually inversely proportional, is going actually downward. The more you have temperature, the rate constant will actually go down. The rate is going down. You can see that if it is a straight line on this side, when you increase it, you can find out straight away the rate is increasing by increasing the temperature. Thank you very much.